Hello, everyone. In this video, I am going to be going over the APIM moderation model with mixed variables. So mixed variables within the context of dyadic data analysis are those that are going to vary both within and between dyads. So these are the variables that we often see in dyadic analysis. So in our example, we're going to use depression, and we measure that kind of continuously. I kind of say that with air quotes. Um, and so we are assessing both members of the dyad, and then, of course, we have something like 250 dyads in the sample. And so the male and the female values for depression in this example are going to be different both between partners. So within the same dyad, the male may have a score of 9, and the husband may have a score of 4 on the dyad. But then when you compare the male from dyad 1 to dyad 2, that first male has a score of 4 in the first dyad, and the male in the second dyad has a score of 10. And likewise, for the female, the female in the first dyad has a score of 9, and then the second dyad has a score of 0. Right. So mixed variables are going to vary both within and between dyads. So that makes them, really, for the most part, really common. Those are the things that we really care about, things that we want to know. There's lots of variability to account for. So we try to estimate that variability, because that's what we do, is when we see variation, we try to account for it in some way. So we're going to do that in two different ways within this video. So I'm going to walk you through two different ways of testing mixed variable interactions within the actor-partner interdependence model. All right, so first, for those of you who are not familiar with R, we are going to be using the lavaan package. We are going to be using structural equation modeling. And so the first thing that you'll need to do is, if you don't already, you'll need to install your packages. So when you open up lavaan, or R Studio, I should say, it kind of looks like this. And then this is the first time you're opening it up, then you'll need to install some packages. So you'll go down here in your console, and you will go to install.packages. Then you will put quotes, and then you will specify lavaan. All right, and then you'll hit Command Return. I'm on a Mac, but I believe you'll just hit Enter if you are on a Windows or a PC. And so what this will do is automatically download lavaan for you. It will automatically install it for you, and then it's ready to go. Then you'll just need to kind of load that package so we can run our structural equation modeling. So the second package, and you'll do this identically to lavaan if you don't already have Haven, is to download and install and use Haven, because that allows us to bring over SPSS data files. And I found this to be the most cohesive way. There are a variety of other ways to bring data over from SPSS into R, but again, this is the most seamless way. All right, so before getting started, we have to do one more thing, and that's set our working directory. Oops, I don't want to hit print. So we'll go to Session, and then we'll go to Set Working Directory, and then we'll go to Choose Directory. And then you will go find the folder that where your data file is stored. And then you're going to set that as your working directory. So that is telling lavaan, go find this data file in this specific folder. All right. And so we will run those. So to load your packages, you just type in library, and then type in Haven and lavaan. You should know that R is fairly finicky with quotations and with capitalizations. So it will be really important to pay attention to caseness within lavaan. Otherwise, you're going to get some error messages. All right, so you hit run, and then down here, it tells us that it loaded Haven, it loaded lavaan, and it created our data object. All right, so we can actually take a look at it. And so if we go over here to my data, you click on it, and then this will give you access to your SPSS data file within RStudio. All right, so this is the data file. We don't really need that for right now, but it is a nice feature to have, especially since R can be finicky with capitalizations. It's nice to have your data easily accessible. All right, so the first interaction model that we are going to run is again, the mixed, where you have a mixed moderator. And that's the variable that varies within and between dyads. And so the syntax is going to get fairly lengthy in terms of creating the interaction terms, and we're going to be creating quite a few. So first, we're going to have our dependent variable, which is relationship quality for males. So couple satisfaction index, underscore comp for composite, then underscore M for male. And then we have our depression score, and then which is are going to be our independent variable. And then we have to do that. We have that for both men and women. And then we have relationship attributions or negative attributions. So we have that will be our mixed moderator for both. And then you will see that we have 4 interaction terms. And so within lavaan, one of the ways, and there are several, to create interaction terms is to do your IV or your moderator, doesn't really matter because it's multiplication, colon your other variable, your independent variable or your moderator. So this is creating the interaction term within lavaan. And so because the moderator's mixed, what we can have actually a series of a bunch of different possibilities for interaction terms. So we have depressive symptoms, and that can vary from men. And so we could have a interaction where the male depression is interacting with male negative attributions on the RAM, and that can predict both male and female levels of depressive symptoms. Right. So the interaction term that is created is going to predict both male and female outcomes. All right. And you might actually be surprised that we actually find some really interesting stuff when you do moderation with mixed variables. For example, I'm working on a project or finishing up a project where we looked at twins, and they were dizygotic opposite sex twins, and we looked at sibling perpetrated abuse, family strain, and how does that predict mental health over a 10-year period. And we didn't find any actor-oriented interactions. So it wasn't, my levels of victimization multiplied by or interacting with my levels of family strain that predicted my mental health. Rather, it was my experiences of sibling abuse by my opposite sex sister. So in my case, a sister interacting with my current perceptions of strain. And that actually predicted the sister's outcomes for mental health. So she actually had worse mental health when she perpetrated more abuse in childhood, and her sibling, the male, perceived that there was a lot of family strain in the family contemporarily or currently. So you can find some really interesting things. So the take home message should be is don't just simply exclude these interactions terms if you don't believe that they are of our interest, because one, they might actually be of interest and they might come out to be significant, or two, they're going to account for variance in your dependent variables. So you're actually going to get a more precise estimate of your effect sizes for the interaction terms when all the interactions are estimated. So again, even if they are not of interest, you need to leave them in your model. So we're going to have 4 possible interaction terms. We're going to have male attributions times male depression. We're going to have male attributions times female depression. We're going to have female attributions times male depression, and we're going to have female attributions times female depression. And we are going to have that for both partners. So you will see this highlighted syntax is for males, and then this syntax now highlighted is for females. And the only thing different between these lines is the underscore M on the dependent variable. Otherwise, they are identical. all right? Because we want the exact same thing to be happening for the male partner and the female partner in this syntax or in this model. And so all of this information is going to be stored in this object, which I'm calling mixmod. And so you can name this really whatever you want and then do an arrow. And then between the two quotation marks, you will have your model. All of this. You will notice that I correlated the dependent variable to account for the non-independence. What you will notice is I did not do that for the independent variable. So in lavaan, all of your exogenous predictors or variables are going to be automatically correlated with one another. So when lavaan goes to calculate your degrees of freedom, it's actually going to take all of that into account, but you will not see that in your results, right? At least in this model, it's not really of substantive interest. What is the covariance between all of your variables, particularly when we have interaction terms in there, you're gonna get some pretty high covariances sometimes. So they're not really all that meaningful. We just kind of need to know they're there, and we actually need them in the model in order to accurately interpret the effects of our main effects and of our interaction terms. All right, next we are going to specify what we want lavaan to estimate and what we want lavaan to give us. So first, we're going to create a fit object. And so I'm just calling it fit.mixmod. And so you'll notice, if you've seen my other videos, a pattern where I name my model up here, and then I just transpose it down here and just add fit dot in front of. And that's my fit object for this model. We have sem, which is a function within lavaan. It also has a growth function, I believe, as well as a CFA function, but SEM is the most general function in lavaan. And, most, if not, I bet like 99 or 98% of the features and the options within SEM are the same for the growth and the CFA. But since we're not really doing a factor analysis, we're not using latent variables at all, we're just using the general sum function to estimate our path analysis. All right, then next we have our model. All right, and then next we have our data. You actually technically don't need data equals my data. This is more than fine, but I have it in here just to just to display that for your purposes. All right. All right. Then we have our estimator, which is ML. Again, this is also a default, but I'll use MLR here because a lot of the times with our dependent variables, they're not going to be normally distributed. And so this is a way to provide a correction to that. And then we also want standardization, and we want the mean structure, which provides you intercepts and means for your variables. Then finally, we want lavaan to print out all of these things, and we have to actually request them. So lavaan by default will give you your chi-square statistic as well as so your unstandardized results. But if you want other pieces of information, then you have to request them. So we want, fit measures. We want standardization or standardized coefficients. Generally, I actually don't use standardized coefficients in interactions. I generally don't report them because I have a hard time understanding what an interaction term is in the context of standard deviation units. When you're multiplying one standard deviation times another standard deviation, it begins to get a little too abstract, but I kind of know what the scaling of my measures is. I know what the min and the max and the range of the CESD and the RAM and the CSI. So to me, it makes a little bit more sense kind of conceptually to use the unstandardized results, but I always include standardized equals true just to get a general sense. And then R squared equals true. So I want to know how much variance is accounted for by the model. So before running this, I accidentally hit Control Z one too many times. So we'll fix that. And we will go ahead and run this model. All right. So this is a saturated model, so we should have 0 degrees of freedom. And it turns out that we did. All right, so we did, we have correctly specified our model because all of the parameters that we could estimate have been estimated. So you will see our model fit in terms relative to the baseline model. Our model going to fit perfectly because we're, again, freely estimating all our variances and covariances. But this gives you a sense of kind of how bad our model would be if we didn't estimate any covariances or any regression coefficients. So we only had a mean and we only had a variance for all the variables in our model, but absolutely, again, no covariances and no regression coefficients. And as you can see, it would be a horrible fitting model. Here you can also see kind of the importance of using robust maximum likelihood when you have non-normal data. So, but without going into too many details, what robust maximum likelihood does is it estimates the extent to which your data are non-normal. And then it provides a correction, which is called a scaling correction factor. And it goes in and adjusts your standard errors. So your standard errors are most likely to get higher because when you have non-normality in your data, it can actually decrease your standard errors and increase your test statistics. So you run into type 1 errors. So we don't want that to happen. So we use the scaling correction factor, and we actually have some pretty decent non-normality in our data. And so this would be a little bit higher than I see kind of on average. So this tells us we really need to do that. And here is our chi-square statistic without it. And here's our chi-square statistic with it. So we can see, even though we don't really care about the baseline model, the implications for model data fit using robust maximum likelihood are actually really, really important because our chi-square goes down by 90, so which is really, really substantial. All right, that goes down by 30% or more. All right. So we'll scroll down. Our CFI and our TLI are going to be 1. Our RMSE and SRMR are going to be 0 because our model perfectly fits the data because we are perfectly replicating the variances and covariances and means within our empirical data set because we haven't imposed any restrictions. So regressions is where we're going to live. So these are going to be our findings. And I will tell you right now, if we were trying to write these up for publication, I would not necessarily have major concerns, but I would want to be doing some poking around, and you'll see what I'm talking about here in a moment. All right, so within the results, you see here, we have our kind of our main effects. I don't find main effects to be particularly interpretable when there's interactions due to the covariances that we are not going to see between all the exogenous predictors. So I don't really know kind of what these regression coefficients kind of mean when we're inducing multicollinearity through the creation of interaction terms. So I'm really only looking at the interactions. All right. And so here we have our unstandardized in this estimate column. Here's our standard errors, our z-value, as well as our p-value right here in this column. All right. And then we have our partially standardized effect sizes, where we only standardize the latent variable or the dependent variable, I should say. And this will be really effective when you have dichotomous indicators, but that is not the case here. So we're going to kind of breeze past that. And we have our completely standardized results. All right, so this is where you standardize your X and your Y. So as you can see for males, we have just about nothing that is significant within the interaction realm right here. So again, and this one's kind of close, but not really. That's pretty far away from 0.05. So we're not going to even interpret that as marginally significant or approaching significance or anything like that, right? So down here for the women, again, that was for the men. We are going to take a look at the interactions, and we are much more successful here. And so you can see we have two significant interactions, and this is when female. So I'll kind of interpret it. We're not going to do plots in this video. So if you want to learn how to do interaction plots through like ggplot, there are plenty of other resources for that. But this is more just the estimation of the mixed variable APIM with moderation. And so as the value of this interaction term gets higher and higher and higher and higher, so a 1 unit increase in the interaction term leads to a 0.023 unit increase in relationship quality, and the p-value is significant. All right. So again, you would have to plot this in order to get the exact interpretive results, because otherwise you're kind of speculating about what the interaction is going to look like. But we know it is significant. So this means that there is kind of a partner level interaction here, that as male depression kind of increases and female attributions increase. So actually here, actually, as male depression, there's a negative effect right here, and there's a negative effect here. So again, you multiply them together, and it's going to give you a positive effect. And so this is going to clearly influence relationship quality. So my guesstimate, if I were to look at to kind of speculate what the interaction plot would look like, it would be, as males' depression gets higher and higher and higher, and relationship attributions get higher and higher and higher and higher, it's going to have an effect on relationship quality. All right. So that would be kind of my guess. I would guess it would kind of fan out where at low levels of depression, the slopes are going to be really, really similar. But as you get further and further away, as RAM increases, as depression increases, the effect on relationship quality increases. And so interestingly, we have the exact opposite happening for women when in relation to their own negative attributions and their own levels of depression, where there's a negative effect on the relationship. All right. So again, a 1 unit increase in the interaction leads to a 0.022 unit decrease in relationship quality. And so earlier I had said that I'm kind of a little worried around these values, and if I was kind of writing this up for publication, I would definitely include some covariates. I would be poking around to see if there's kind of some multicollinearity going on. And what tells me that is that we have some pretty extreme standardized effects. So these are a pretty substantial data weight. So a 1 unit increase in the interaction term leads to a 1.19 unit increase in relationship quality for women. So again, that seems extraordinarily large. And when we have 4 interaction terms within the model, it would not surprise me if we have some multicollinearity. One of the things that you could do that I did not do in this is you could center your variables. That's one of the ways that centering is actually effective, but it will actually not change any of your estimates or your p-values or anything like that. All right. So it will not change the interpretation, the effect size, or anything like that of your results, but it can reduce multicollinearity. So that would be one thing that I would do if this was more for conference presentation or a manuscript. But again, this is just for demonstration purposes, and so I will just kind of leave that be. And down here is the other thing that we really care about, and that's going to be our square, which is the amount of explained variance. And as you can see, our model is doing quite a good job at explaining variation in relationship quality for males and for females. All right, so now we're going to move to our second mixed variable APIM, and this one is far simpler. This is going to be what's called an actor by partner interaction. And so rather than adding in two variables, because in the previous model, we had included relationship attributions for males and relationship attribution for females, which led to all of the different interaction terms. We are not going to add any other variables. Rather, what we're going to do is just multiply the IVs for each person by one another. And that's going to be the interaction term. And so what this allows us to do is that we can kind of play out, when males depression is getting higher and higher and higher, and female depression is getting lower and lower and lower, what happens to relationship quality for both partners? I think that's a really interesting question. The dynamics of one person being quite depressed and the other person being not depressed at all. How does that influence the quality of the relationship? Or is it, as both members of the dyad are getting more and more and more and more depressed, that relationship quality goes down, right? So is it that it's the common experience of depression that really negatively affects the relationship? And then you can also constrain paths to equality. And so you can say, is the interaction significantly different for males and females? So we can do a lot of really creative things that can get at a lot of nuance that dyadic research, I really wish they would do more often. All right. And so I will actually simplify the syntax. I have it kind of written out in a fairly extensive way. We don't really need all of those covariances again. So we're just going to do something that's way simpler. And so what you'll notice here is I just create an interaction term multiplying male depression by female depression. And I have the exact same model for males and females. And then I have that residual covariance for relationship quality, since lavaan does not automatically correlate your residuals for your dependent variables. They only do that on the X side of the equation. Everything else is copied and pasted from up above. So we will take a look and see kind of what we have here. So again, we should have no degrees of freedom. Actually, I am going to rerun this. I'm going to throw robust maximum likelihood on there just to be safe, because we saw in the previous model that we probably need it. All right. So here are the results. Again, we have, as you can see, a pretty substantial decrease in the chi-square statistic with maximum likelihood versus robust maximum likelihood. So again, it's telling us we probably need this in our model, right? So fit statistics are going to be null. You're not going to be able to evaluate model data fit. And what you will see here is that we have some significance. So we actually, everything is significant. And so we find that depression affects both partners, right? So if I'm paired with my partner is, let's say her name, let's say her name is Shelley. The more depressed I am, the more depressed the lower quality relationship I have, or I evaluate my relationship to be, and the lower quality that Sally represents our relationship as my depression gets higher and higher and higher. And likewise, when Sally's level of depression gets higher and higher and higher, she rates the relationship to be more negative. And when the more her depression gets higher and higher, the more I rate my relationship to get lower. So it's doing the effects that we would expect, right? We also have the interaction, and so we have again, not surprisingly, a positive interaction here. And so when you multiply two negative numbers together, it's not shocking that you get a positive number. And so we would have to plot this in order to really obtain accurate interpretations of depression. All right. So I'm not going to go ahead and interpret it. We can just see that it's highly, highly, highly significant. And again, I'm suspecting there's some multicollinearity or something else going on with these really large standardized regression coefficients, but that's for more of a sensitivity analysis, more of checking model assumptions, and things of that nature, and less so a part of this demonstration. And then finally, we can go down here and we can look at our R-squareds, and they are very, very similar. So the final thing that we will do is we're actually going to compare, since I ran it with and without maximum likelihood. We'll take a look at the estimates as well as the standard errors and see what kind of happens when we don't have a robust maximum likelihood kind of being the primary estimator. So we notice that all of them are significant, but you notice that the p-value here is quite a bit smaller, all right? And you also see that your standard errors are quite a bit smaller. So the largest standard error is 0.106, looks like. 106 and 101, and then 83 and 87. So we'll scroll back down to our previous or our model with robust, and you can see there's not much change here. But what we can see is here there is a decent amount of change in our standard errors. So we're lucky in this case that we have a really highly significant p-value. But if this p-value here was, let's say, 0.03, and with maximum likelihood, and then we throw a robust on there, this might slip past p equals 0.05. So in this case, we probably wouldn't change a whole lot. I definitely feel more comfortable with robust maximum likelihood on here, but it can actually have far more serious implications in other models where p-values aren't as low as they are in this model. And you can also go up and compare the estimates. And what you'll notice is they are identical. They are exactly the same. So negative 665,373, 665, and 373. So your estimator is not going to change your parameter estimates. Rather, it is going to change your standard errors, which is going to change your z-value, which is going to change your p-value. Right? So your estimates are going to be unbiased in maximum likelihood and robust maximum likelihood, as long as the other kind of assumptions and properties of maximum likelihood are coming online, like a sufficiently large sample, things of that nature. But it will just affect your standard errors when you change your estimator. So hopefully this has been interesting and helpful to you in looking at mixed effects within the actor-partner interdependence moderation model.